We are in Chapter 5, Integration. Section 5.1 is Indefinite Integration and Differential Equations. Derivatives provide information on rates of change and allows us to find extrema of a function. It is not always possible to find a ready-made function that provides information about the total amount of a quantity, but it's often possible to collect enough data to come up with a function that gives the rate of change of a quantity. The reverse of finding a derivative is known as anti-differentiation or the antiderivative. The first example says if f of x equals 7x, then f prime of x equals 7. So f of x equals 7x is an antiderivative of f of x, which equals 7. Likewise, if we have the next example says if f of x equals x cubed, then f prime of x equals 3x squared, which is what we've done before. So then f of x equals x cubed is an antiderivative of f of x equals 3x squared. All antiderivatives of the function f are of the form, this is the integration symbol. The integral of f of x dx equals f of x plus c. The s that looks stretched out is our integral sign. F of x is the integrand, what we're taking the integral of, and the integral of f of x dx is called an indefinite integral. So an indefinite integral says if f prime of x equals f of x, then the integral of f of x dx is equal to f of x plus c for any real number c. So we have some rules for integrating common functions, and the rules from derivatives are very useful to know for going and finding antiderivatives, since they're going to be almost like the opposite of one another. So the better off that you know those rules from Chapter 2, the better off you'll be with Chapter 5. So the first rule we have is called the constant rule. It says the integral of k dx is equal to kx plus c. If you were to take this function right here that I've circled and take the derivative of it, you would be winding up with that integrand that we had at the beginning. The next rule is called our power rule. The power rule says the integral of x of n dx is equal to x to the n plus 1 divided by n plus 1. And this is provided n does not equal negative 1. And then we have a plus c, which is just a constant. And then we have our natural logarithmic rule, which is the integral of 1 over x dx is equal to ln of the absolute value of x plus c. The reason why we have those absolute values on there is because x, we can only be taking the log of, has to be something greater than 0. Then we have our natural exponent rule, which is the integral of e to the kx equals 1 over k e to the kx plus c. Again, k cannot equal 0 because we're dividing by it. So this c is just a constant. A constant is just a number, and remember when you take the derivative of a constant, you'll be able to get that as 0, and it's like it never mattered. So you could take all of these, and if you were to take any of these ones that we have on the right side and take the derivative of these, you will wind up with that integrand that we had here. So check that on your own and to make sure that you're okay with those formulas. Definitely something that we need to know. Go ahead and erase those. The next example that we have says find each indefinite integral. The first one that we have is the integral of x squared dx, and this will be using our power rule. So we're going to go ahead and add 1 to our exponent. I'll write it out a little bit more this time. Divided by that same value that we have as our exponent, and then don't forget your plus c. Make sure to simplify this. You can write it as 1/3 x to the third, or you can write it as x to the third over 3 plus c. Make sure not to forget your plus c's. You can always check this, and to check this you would take the derivative. So d dx of 1/3 x cubed plus c, which was our answer. And so when you do this, your 3 would come out in front. You'd have 3 over 3 x to the second plus 0, which would just equal x to the second, which checks to what we had in our original problem up here of our integrand. Part B, says the integral of 1 over t cubed dt. I'm going to go ahead and rewrite this as t to the negative third dt. So taking our integral, I am going to add 1 to my exponent. So we have negative 3 plus 1, dividing by the same thing, and then plus c, which is our constant. This simplifies to, the denominator is going to be negative 2, so we'll say negative 1/2 t to the negative second plus c. And again, not having a negative exponent, this is going to be rewritten as negative 1 over 2t squared plus c. For c, we are going to rewrite this as the integral of x to the 1/2 dx. So when we go ahead and do this, same idea. I'm going to take my value, take my exponent and add 1 to it, and divide by that same value that we have, plus c. X to the 1/2 plus 1 is going to be x to the 3 over 2. And usually when we do these, we leave our exponents as improper fractions. And then 1/2 plus 1 would be also 3 over 2 plus c. We can, from here, multiply both top and bottom by the reciprocal of the denominator and multiply by 2/3. And we end up with 2/3. And we have x to the 3 over 2, which is going to be the square root of x to the third plus c. Part D, which we have on here, is going to be the integral of, if you notice there's nothing here, so if you want to think of this as being the integral of 1 du. And so when we integrate this, you can think of this also as being the integral of u to the 0 du. The reason why is because u to the 0 is just 1. So using the same idea for the power rule, adding 1 to our exponent and dividing by that same value, and then plus c, we will get u to the first over 1 plus c, or just u plus c. Again, you can check all of these by what I've boxed as our final answer and take the derivative of them to see if you get that integrand. We have a couple more on the next page. So looking at E and at F, we're going to go ahead and circle E and we'll work on that one together in class. And then F says the integral of, we have e to the 3x plus 1 over x. And so e to the 3x, if you go back and look at your rules, it's going to be 1 over 3 e to the 3x plus, and then the antiderivative of 1 over x is going to be ln of the absolute value of x plus our constant c. And that would be all that we can have. Again, you can check this by taking a derivative. So you can do that, which is nice for when you have an exam. Right below this, we have the algebraic rules for indefinite integration. Says let k be any constant. Then we have the constant multiple rule, which says that the integral of k times f of x dx is just equal to, and you'll notice that constant is just moved out in front. We're able to integrate the rest of it the same. And then we have our sum and difference rule, which says that if we have multiple terms, we're able to integrate each one individually. And that's what we did up above in the last two examples with E and F. So the next example that we have says find each integral. And so since we have a 5 on this one, we are able to move that out in front and say the integral of 5t to the 4th dt is equal to 5 times the integral of t to the 4th dt. And we have our 5 would just stay there, adding 1 to our exponent and dividing by that same value, plus c. And then we would simplify this to being 5 times t to the 5th over 5 plus c. Your 5's would reduce and cancel out. And we have t to the 5th plus c. Again, you could take your derivative of this and check to see if it's correct. Part B, I'm going to go ahead and move that 3 out in front and rewrite this as the integral of u to the -5th du. Same idea, that 3 stays there since it's a constant multiple. I have -5 adding 1 to the exponent, dividing by that same value in the denominator, plus c. Cleaning it up from here, we have 3 times u to the -4th, all over -4 plus c, which again we can simplify a little bit more and say this is -3/4. That u would move to the denominator since it is a negative, so I'll put u to the 4th in the denominator, and then plus c. Again, check by taking the derivative of this. Part C and Part D, we will go ahead and circle and work on those two together in class. The next thing that we have says an indefinite integral of additional exponent functions. We'll go ahead and start this. Here's some more formulas that we need to know. It says for a greater than 0 and a not equal to 1, the integral of a to the x dx is equal to a to the x divided by ln of a plus c. And then the integral of a to the kx dx is equal to a to the kx divided by k times ln of a plus c, and k cannot be equal to 0. We have some additional examples on the next page. The example at the top of the next page says find each integral. We have the integral of 5e to the x plus 6 over x dx. Taking the integral of each of these individually, 5 is just a constant. Integrating e to the x dx is just e to the x. Plus 6, which is just a constant, times 1 over x dx. The integral of that is just going to be the natural log of the absolute value of x. Again, indefinite integrals, we put our plus c. The next integral that we have, part B, is the integral of 3e to the 4t dt. Since 3 is just a constant, I will leave that there. Integrating e to the 4t, it's going to be e to the 4t divided by 4 plus our constant c. You can, if you would like, just rewrite this as 3 over 4. It's the same thing, you can't really simplify it. 4t plus c. The next one that we have is the integral of 2 to the -4u du. And the integral of this is going to be equal to, looking at the formulas that we had previously, as 2 to the -4u divided by -4 times ln of 2 plus c. Not much we can do with simplifying here, so I'm going to go ahead and leave that. Part D, we are going to go ahead and circle, and we'll try that one together in class. Next thing that we have says remember that marginal cost, revenue, or profit is the derivative of the cost, revenue, or profit function, and if the derivative of the cost function c of x is c prime of x, this would imply that the integral of the derivative is just going to be equal to that original cost function. First example that we have says find the cost function from the given marginal cost function, and we are given our marginal cost function. It also tells us the fixed cost is going to be $10, so we'll get into what that means in just a sec. So I need to integrate my marginal cost function. So integrating my marginal cost function with respect to x, since that is my variable, will be equal to our original cost function plus, I'm going to call it c naught. This c naught here is going to be our fixed cost. And I called it c naught just because I don't want you guys to get confused with the c for cost and the c for the constant. And so we need to integrate our derivative, or our marginal cost function, which is 0.2 x squared plus 5 to the x. Do not forget your dx. Again, it is incorrect if you do forget that. So the 0.2 is just a constant. And then we have x to the third divided by 3 plus 5, which is our constant, x squared divided by 2 plus, again, I'm going to call it c naught this time. And so with our c naught, this is our fixed cost, which is just $10. I'm going to go ahead and simplify this. 0.2 divided by 3 on your calculator, you can leave it as a decimal, or you can rewrite it as a fraction, which would be 1 over 15. X cubed plus 5 over 2, x squared plus c naught, which is 10, and this is going to give us our original cost function, so I'm going to call that c of x. The next example that we have says a manufacturer has found that the marginal cost of a certain product is 3q squared minus 60q plus $400 per unit when q units have been produced. The total cost of production for the first 2 units is $900. What is the total cost of producing the first 5 units? So again, we are given a marginal cost function, which is listed there, 3q squared minus 60q plus $400. And so this was going to be our prime. I'm going to go ahead and call this c prime of q, since q is my variable. And this is 3q squared minus 60q plus 400. And so we need to integrate this. So we're going to integrate in order to get our cost function, which is going to be the integral of 3q squared minus 60q plus 400 dq, since that's my variable. Integrating this, going term by term, 3 is a constant, times q to the third divided by 3, minus 60 times q squared divided by 2, plus 400q. Again, I'm going to put a plus c when I'm going to call it c naught this time, which is our fixed cost. I do not know the fixed cost this time around, but I do know that the first 2 units is going to be $900. So that means that this total amount that we would have for our cost, again, this is our c of q, it's going to be $900 when q is equal to 2. So when q is equal to 2, because again, q is our number of units. You can see that up above too, q units. So this is going to be 2 to the third minus 30 times 2 squared plus 400 times 2 plus c naught. Working this out, you arrive at a value of c naught is equal to 212. And so our function is going to be c of q is equal to, and it's q to the third, minus 30q squared plus 400q plus 212. And again, it wants us to find the total cost of the first 5 units. And so to do that, we need to find c of 5. I'm substituting in 5 into my function. We end up with 5 to the third minus 30 times 5 squared plus 400 times 5. And then also don't forget that fixed cost of $212. Working this out, we get a total of $1,587. So this says, what is the total cost of producing the first 5 units? And that's going to be $1,587. Section 5.2 is integration by substitution, which is a very challenging section for students. So definitely something that you want to get an early start on with the homework, and reach out for any questions that you might have to either me or the Teamwork or the ASAC or any other tutoring services that we have on campus. So 5.2 is integration by substitution. One of the most common methods of integration is called substitution method, or we also call it U-sub or U-substitution. We can think about this as the chain rule in reverse, or the method for undoing the chain rule. So as a reminder, there's the chain rule there. If you remember, we had an inside function and an outside function. And so we took the derivative of this by taking the derivative of the outside, leaving the inside the same, times the derivative of the inside. So we have the substitution rule. Give that a star. This says if u equals g of x is a differentiable function whose range is the interval I and f is a continuous function on I, then the integral of f prime of g of x times g prime of x dx, and notice that g of x is our inside function, then this is just going to be equal to the integral of f of u du. The next thing that we have is integration by substitution, or the end chain rule. It says notice the problem is a composition of a function. So noticing that there is a inside function and an outside function, and also the integral is of the product. First thing that we need to do is identify the inside function. Let the inside function equal u. Next is going to be finding du from u, which involves taking a derivative. Solve for dx. substitute in u and dx into the original problem and simplify. Then we are going to integrate. Next thing we do is we're going to back substitute for u into the solution. And then the big one here is checking by taking a derivative of the solution. So you can always check your work, which is great for exams and quizzes, by just taking a derivative. So the first example that we have on here is set up a little different. So it's going to work us through those steps one by one. And then after this, we'll do another one just to kind of review it. And then from there on out, it's just going to be written as just a single problem, and you're going to have to recognize and do those steps on your own. So the first thing is noticing that we have an inside function and we also have an outside function. So the inside function is that 4x squared plus 1. And if you notice, the derivative of this is equal to 8x, which you'll notice too is also in the product of your integral. So those are some key things to look for when you're using substitution method. So first thing is, step one is letting u equal the inside function. Our inside function here is 4x squared plus 1. And so I'm going to take this integral for this problem and I'm going to rewrite it. It's now going to be 8x u to the 5th dx. From here we have an issue. The issue is that you have x's and u's in your problem at this time, and we're unable to integrate it right now in doing anything along those lines. So the next step says to find du from u. So what we're going to do is we're going to differentiate. We're going to take the derivative of u with respect to x. So that's du dx. Taking the derivative of our function up above, that's just going to be 4x squared plus 1. Derivative would be 8x. And I'm going to rewrite this as multiplying both sides by dx. It's going to be du is equal to 8x dx. So next thing that we need to do is to solve for dx. And to solve for dx, we need to divide by 8x. So dx would be equal to du divided by 8x. It says substitute in u and dx into the original problem. So my integral is now going to become the integral of 8x. We already substituted in u. And dx we just found is equal to du divided by 8x. This is really nice because you'll notice your 8x's are going to reduce or cancel out. And we're left over with the integral of u to the 5th du. So we took something that we were unable to integrate before, the integral of 8x times 4x squared plus 1 to the 5th. We could not integrate at that time. We could if we had multiplied that out, but that would have been taking a lot of work. So what we did is we used u sub and we rewrote this, and now we're at the integral of u to the 5th du, which is a lot easier to integrate. So the next thing says integrate and don't forget your plus c. So this is going to be equal to 1 over 6 u to the 6th plus c. Next thing is to back substitute in u, and remember u is equal to 4x squared plus 1. And so this is going to be the same thing as 1 over 6, and then instead of u we're going to write 4x squared plus 1 raised to the 6th power plus c. And then the next thing that we have says to check by taking the derivative. So taking the derivative of our function that we have right up above, it's going to be 1 over 6 times 6 times 4x squared plus 1 to the 5th, that's that chain rule, times the derivative of the inside, which is just going to be 8x, plus the derivative of a constant is just 0. You'll notice that your 6's reduce out. We'll put the 8x in front, and I have 8x times 4x squared plus 1 raised to the 5th. And checking up above for the original problem that you have, this does equal our integral that we had up above, so check. So you can always check by taking the derivative of an antiderivative and seeing if your answer is correct. The example on the next page, we're going to work out the same way with the same steps. So for this one, again, we're going to let u equal our inside function, and our inside function this time is going to be 4x squared plus 8x. And then we're going to go ahead and rewrite our function now as the integral of x plus 1 divided by, and we're going to call that u to the 3rd, and then dx. And again, we have an issue because we have x's and u's, and we're unable to integrate anything that has more than one variable. And so now we're going to take the derivative of our u with respect to x. We're going to have du dx, which is going to be 8x plus 8, which we can also factor out the 8. And I'm going to have this as du is equal to 8 times x plus 1 times dx. And then solving for dx, I'm going to have du over 8 times x plus 1. And we're going to substitute in u, which we did already, and dx into our original problem. So from here I'm going to have the integral of x plus 1 over u cubed times, instead of dx, I'm going to substitute this part in, and it's du over, and it's 8 times x plus 1. If you notice, our x plus 1s are going to reduce out, and we're left over with the integral of 1 over 8u cubed du. So from here, I can pull that 1/8 out in front because it's just a constant. And I'm going to rewrite this as u to the -3rd du. Next step says to integrate, and don't forget your plus c. So the 1/8 is going to stay there. Adding 1 to our exponent, we end up with u to the -2 divided by the same value, -2 plus c. Simplifying this, we end up with -1 over 16. And I'm going to put my u in the denominator since it is a negative exponent, so u squared plus c. And then we're going to back substitute. U again from up above is 4x squared plus 8x. And we're going to put this back into our solution. So we're going to have -1 over 16 times, and our u value here is going to be 4x squared plus 8x raised to the 2nd power plus c. And this would be our answer that we would have for our integral. And then to check this, we can take a derivative. So taking the derivative of this, we have -1 over 16 times, and I'm going to rewrite it as 4x squared plus 8x to the -2nd plus c. And taking the derivative of this with respect to x is going to be -1 over 16 times -2 times 4x squared plus 8x. And that would be to the -3rd times the derivative of the inside function, which is going to be 8x plus 8. Derivative of c is just going to be 0. From here, if we were to simplify this, I would have, if you factor out an 8, you would have, and I'm going to use this space over here, we have -1 over 16. And factoring out the 8 here times -2 is going to be times -16. And then we have a 4x squared plus 8x to the -3rd. And then left over with x plus 1. The 16s would cancel, the negative signs would cancel, and we're left over with x plus 1 over, and I'm going to put this in the denominator, which is going to be 4x squared plus 8x to the 3rd power. And if you look back up above, that is what we had in our original function, so check. Right below this, we have some more integration problems. This is more like how you will see them, and those steps you need to kind of keep in your head. Good thing to write on your outline to have for an exam and to study so you know how to integrate by u substitution or by substitution. So the first one here, I'm going to let u equal my inside function. My inside function this time isn't maybe as clear, so I'm going to let it equal the denominator. So I'm going to say let u equal x squared plus 6x. And when you take the derivative of this, I'm going to go ahead and rewrite this as du equals, and if you notice, we were multiplying both sides by dx, and so I'll just put that on the other side right away. And this is going to become 2x plus 6, and then dx. From here, I can factor out a 2. and I wanted to solve for dx. So I'm going to go ahead and write dx is equal to, and it would be du divided by, factoring out the 2, I would have x plus 3. If you need to show some extra steps there, make sure you do. So for this problem, I'm going to have the integral of, and it's going to become x plus 3 divided by u, since that's what we let the denominator equal, and then dx is going to be the same thing as du over, and it's 2, parentheses x plus 3. Our x plus 3's are going to reduce, which is nice. I have a 1/2 that I can pull out in front of my integral, and I have 1 over u du. So if you remember from before and up above on beginning first few pages, we had the integral of 1 over u du is the same thing as ln of the absolute value. So we're going to have 1/2 times the natural log of the absolute value of u, and don't forget your plus c. And again, from here we need to back sub. So I'm going to have 1/2 ln, and instead of u, we will put x squared plus 6x. So the absolute value of x squared plus 6x plus c. You can check this, and I'll leave that for you to check on your own, but you can check by taking the derivative. So by taking the derivative. And it's a good thing to do on exams and on quizzes, so that way you can check to actually make sure that you did the problem correct. The next example that we have, I'm going to go ahead and let u equal our exponent. And if you notice, that is our inside function on the exponential e, so we have x to the 4th. You also notice that you have the derivative of x to the 4th, which would be an x to the 3rd with a coefficient, and that is also in the problem, which makes it nice. So from here we have du is equal to 4x to the 3rd dx. Solving for dx, we are going to have dx is equal to du divided by 4x cubed. So this problem is now going to become the integral of, and we have x cubed e to the u times, and dx is going to be du divided by 4x to the 3rd. And if you notice again, our x to the 3rds will reduce. I'm going to pull the 1/4 out, so it's going to be 1/4 the integral of e to the u du. And notice again that we now only have one variable, which is u, which makes it, we're able to now integrate. And it's a nice function to integrate. The integral of e to the u is just e to the u. Don't forget your plus c. From here we do need a back sub. And so we have e to the, and it's x to the 4th, plus c. And this will be our integral answer. Again, we can check. I'll leave that up to you guys to do on your own. So we have some more examples on the next page. So looking at the next example that we have, it says find the integral, and it's the parentheses 1 plus 5 ln of x to the 2nd power all over x dx. So our inside function is that 1 plus 5 ln of x, and so I'm going to let u equal taking the derivative. Derivative of 1 is just 0. And then we end up with 5 over x dx. So now solving for dx, I can multiply by both sides by the reciprocal of 5 over x, which would be x over 5. And so our derivative is going to be x over 5 du when I multiply by that reciprocal. So our problem here is going to become the integral of, and the numerator is what we had set for u, so it's going to be u squared over x times, and then dx is going to be the same thing as x over 5 du. So if you notice here, your x's are going to reduce out. We have two variables there, which makes it impossible for us to solve. But once you cancel out those x's, you'll notice that your integrand is just going to be left with u's. And so I have a 1/5 that I'll pull out in front of my integral. We have u to the 2nd du. Integrating this, we have adding 1 to our exponent would become u cubed, divided by the same value, plus c. And so this is going to work out to be 1/15 u to the third plus c. And then I have to back sub, and I'm going to have 1/15 u, which was 1 plus 5 ln of x raised to the third power plus c. And this is our final answer. Again, you can check by taking a derivative to make sure that you did that problem correct. We have 3 more on this page, and I'm going to go ahead and circle these 3 so we can work on these together in class. But definitely if you want to try to get started on these on your own, and at least see if you can pick out what the inside function is, like what would you let u equal, and then kind of going from there, that would be helpful to kind of understanding these problems and how to attack and start them on your own. The next example says the resale value of a certain industrial machine decreases at a rate that depends on its age. When the machine is t years old, the rate at which the value is changing is going to be negative 960 e to the negative t over $5 per year. Express the value of the machine in terms of its age and its initial value. So in order to do this, this is our rate. Remember, a rate is a derivative. And so to get the expressing the value of the machine in terms of its age and initial value, we will have to take the integral of that rate, which is going to be negative 960, and it's e to the negative t over 5. And our variable is t, so with respect to t, which is our time, in order to integrate this, I need to let u equal our inside function, which is going to be negative t over 5. I'm going to rewrite as negative 1 over 5t. Same thing though. Taking the derivative, so du is just going to be negative 1/5 dt. Solving for our dt this time, it's not a dx. I would multiply by the reciprocal, and I get negative 5 over 1, or just negative 5 du. So this problem is now going to become, and we have the integral of negative 960 e to the, and that's our u value, times dt, which is going to be negative 5 du. If you notice now we have all variables of u, so I can multiply negative 960 and negative 5, and I'm going to pull that value out in front. That's going to be 4,800. And we have the integral of e to the u du, which again works out very nicely. So we have 4,800 e to the u plus c. And I'm going to back sub this. So we have 4,800 e to the negative t divided by 5 plus c. And so this is the value, express the value of the machine in terms of its age, which is t, and its initial value, which would be our c. So from here, I'm going to just rewrite our function a little bit nicer. This is value is equal to 4,800 e to the negative t over 5 plus c. Part B says if the machine was originally worth $5,200, how much would it be worth when it is 10 years old? So with this value, it says if it was originally worth, that would be when time is 0. And so when time is 0, the value would be equal to $5,200. So our value is $5,200 is going to be when t is equal to 0. So substituting this in to my equation, negative 0 over 5 plus c, I'm able to figure out that fixed cost or fixed amount that we would have. And so from here, e to the 0 is just going to be 1. So we have $5,200 equals 4,800 plus c. And so c is going to be 400. So the value of the machine, that fixed amount, would be 400. And so v, so our new function is going to be 4,800 e to the negative t over 5 plus 400. And then I have to find what happens when it is 10 years old. And when it's 10 years old, that means t is going to be equal to 10. And again, we are measuring our t value in years as stated up above. So if I substitute in 10, I'm going to have 4,800 e to the negative 10 divided by 5 plus 400. And you can rewrite that as a negative 2. And so substituting this in on your calculator, we would have 4,800 e to the negative second plus 400, which is going to work out to be, and I'm around 2 decimal places since we are dealing with money, which is going to be $1,049.61. So initially the value of this machine was $5,200, but it has depreciated and gone down in value, and that happens with most things that we have. We are in section 5.3, the definite integral and the fundamental theorem of calculus. We can approximate the area under a curve by making equal size rectangles and adding up each rectangle's area. The smaller the width of the rectangles as n gets larger, the more closely the approximation will be to the actual area under the curve, as shown in the figure below. So if you notice, the same curve is drawn 3 times, but we have 4 rectangles here, we have 8 rectangles here, and we have 16 rectangles here. You can tell just by looking at the picture that the more rectangles that you have, the better the approximation is to that area under the curve. It says, when drawing the rectangles under the curve, we can either draw the rectangles from the left endpoint, the right endpoint, or the midpoint where the rectangles touch the curve. It is usually the case where the midpoint rule gives a more accurate answer than either the left endpoints or the right endpoint rule. So the area is equal to the limit as n approaches infinity. And again, that means that we have an infinite amount of rectangles. That's going to be the best approximation for our area. And it's going to be f of x1 plus f of x2 plus f of x all the way through till f of xn. And this is going to be the height of the rectangles. And then your delta x is the width. And so all you're doing is adding up the height. And this is going to be our width. So the area of a rectangle is length times width. And so it says where x of I is either the left endpoint, the right endpoint, or the midpoint of the ith subinterval. If the intervals are from A to B, is divided into n equal parts, each with a length of delta x. On the next page, you can see the left endpoints, the right endpoints, and the midpoints all shown in the diagram. So to find the area approximation, you're going to add up the area of each rectangle, which again is going to be our areas are going to be equal to length times width, which is what we learned in algebra class or even before that. And our length is going to be our f of x, and our width is going to be our delta x. And so we're just going to multiply those all, the height and the width, and that would give us one of these rectangles here. And so again, this would be our width down here, is delta x, and the height of this is going to be our f of x. And again, depends on the ith. We're going to do that each time, so the ith interval. And it says, example on the next part says, approximate the area under the graph of f of x and above the x-axis using the following method with n equals 4. It says part A is the left endpoints, B is the right endpoints, and C is the midpoints. So in order to do this, I'm going to go ahead and look at what my graph is, and my graph is just going to be x to the second, and we're only going from 1 to 5. So I'm going to go ahead and draw the graph. And if my x values only go from 1 to 5, then I know that my y values are going to be going from 1 to 25. So I'm going to go out to 5. 1, 2, 3, 4, and 5. Label those. And then I'm going to have to go all the way up to 25 at least. So here's 5, 10, 15, 20, and then 25. And if I were to plot this graph, again, we're only starting at 1, so substituting in 1 into my formula, 1 squared is 1, 2 squared is 4, do the best you can on this, 3 squared is 9, 4 squared is 16, 5 squared is 25. So connecting your points in that smooth curve, which is our parabola, I have my graph. Again, this does go on farther, but we're only concerned from x is 1 to 5. So part A says to use the left endpoints. So again, left endpoints. And so to use our left endpoints, I'm going to go ahead and draw my rectangles. That means I'm going to start on the left side, go up to 1 and then over to 1. So to find the area of this first curve, I'm going to have to do my width here, which is my delta x value. And I'll write delta x up here. We had a formula on the previous page, which was just b minus a divided by n. And since we have 4 rectangles, I know that I'm going to have 5 minus 1, since this is my a and this is my b. So I'm going to have 5 minus 1, all divided by 4, which is 4 over 4, just 1. And this would be my delta x value, which you can see that in the diagram, so we're counting by ones. So delta x is equal to 1. And so to find the first rectangle, I need to do the width, which is going to be 1, times the height of that, which is f of 1. And I can easily find f of 1 just by substituting that in, and we'll do that next, plus my second rectangle, which also has a width of 1, times that height, which you need to get by plugging in, since it's a left endpoint, plugging in 2, so f of 2, plus the next rectangle, which is going to be width 1, and the height's going to be judged by 3, so plugging in 3, so f of 3. And then my last rectangle is going to have height of f of 4, so plus 1, which is our width, times f of 4. And this just gives me all 4 of these rectangles, and then adding these all up, which is, again, this is going to be 1 plus 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and then adding these all up and multiplying, and we end up with 30. So again, this is our left endpoint, and if you notice, all of these rectangles are smaller than the graph. I'm going to go ahead and switch colors here, and we're going to go ahead and say this is going to be for our part B, which is to use the right endpoints. And so I'm going to start on the right side of my graph, which is going to be starting at that rightmost point, which is going to be 5. I still have my delta x here, which is equal to 1 for all of these, but this time I need to draw from 5 all the way up until I hit the graph, over and then back down. So that first rectangle is going to be 1 times f of 5, plus the next one's going to be 1 times f of 4, using that right endpoint. And then the next one's going to be 1 times f of 3. And then the last one's going to be 1 times f of 2. And substituting these all into a calculator and working this out, we get an area of 54. So a lot of times they'll ask for an under approximation and an over approximation. So if you look at these rectangles that we just put on using the right endpoints, you'll notice that all the heights are above that graph. And so this is our over approximation, because it's larger. And then 30, since all of those rectangles were less than the graph, you'll notice that some of that area is not accounted for. And this is our under approximation. And it just depends on how the graph is. So sometimes the left endpoints will be the over, and other times it'll be the under. Just depends. Okay, so the next one that we have to do is part C. I'm going to go ahead and switch another color. And part C is going to be our midpoints. So this time we are going to use the midpoints, and so that means that we need to look at in between all of these rectangles that we have. So right here we'd have 1.5, we'd have 2.5, 3.5, and 4.5. So this means that starting at 1.5, I'm going to draw up to the graph and over to the left and the right, and I'm going to shade this one just so we can see it a little bit better since there's so many lines on there. So this is going to be, the width is still 1, but my height is now going to be f of 1.5 plus, width is still 1 here, times, but this time I'm going to use 2.5 as my judging point. So I'm going to go up to my graph and shade. So this is going to be, my height is going to be 2.5 plus the next one, which my height is going to be judged by 3.5, so going up until I hit my curve. Once I hit my curve, draw a horizontal line, and I'll shade that. So this is going to be f of 3.5 plus 1 times, and then the last one I have is 4.5, which if you draw a vertical line up, put a dot across, and then shade, we have f of 4.5. If you add up all these values, and again, we need to first substitute in 1.5. So 1.5 squared is going to be 2.25. And then we have plus 1 times, and then substituting in 2.5 into my function, which is going to be 6.25. Plus, and then we have 1 times, and we have the next value, which is substituting 3.5, which is going to be 12.25. Plus 1 times, and then substituting in 4.5, we have 20.25. So multiplying those all together and adding it up, we end up with a total area of 41, which is in between our under approximation and our over approximation that we had from part A and part B. So this is why that midpoint rule is usually the best one to use to approximate the area under a graph. So what's other ways that we could have done to make this a better approximation besides just using the midpoint rule? One way that we could have done that would have been to increase the number of rectangles that we had. So if we had more rectangles, it would have been a better approximation to that area under the curve. The next thing that we have is called a definite integral. The definite integral is going to be the integral from a to b of f of x dx. So we have indefinite that we learned about before, where there was no numbers on our integral sign, and now definite integral, which is where there are numbers. And this gives the exact area between the graph of f of x, the x-axis, from a to b. It also is going to be the integral from a to b of f of x dx is equal to the limit as n approaches a of f of x plus 1 plus f of x of 2 plus all the way through f of x of n times delta x. And this is the next thing that we have. We're going to give a star to. It's the fundamental theorem of calculus. It says assume that f of x is continuous on the interval from a to b and let f prime of x equal f of x on that interval from a to b. Then the integral from a to b of f of x dx is going to be equal to f of b minus f of a. So definitely something we need to know. Next says note that there is no constant c that we need to add, and the reason why is because if you were to evaluate this, you'll notice that your c's would cancel out. And so you can see that down below. It says informally, the fundamental theorem of calculus says we can evaluate a definite integral by solving the antiderivative, and we get our antiderivative by integrating this and substituting in the limits of integration b, and then substituting in a into f of x, and then subtracting. Notice that there's no constant while evaluating a definite integral. On the top of the next page, we have properties of the definite integral. The first thing says, suppose that f of x and g of x are integratable over the interval from a to b and k is a constant. First one says that the integral from a to b of f of x plus or minus g of x dx is equal to, we're able to take the integral of each of those individually. Second one says that if we have a constant, we're able to pull that out in front of our integral, just like what we did for indefinite integrals. The third says that if you're integrating from a to b of k dx, this is the same thing as just k times b minus a, and that's from that fundamental theorem of calculus. Number 4 says that we have the integral from a to b of f of x dx is equal to negative, and we're going to go ahead and switch, there is a mistake on here, b to a. And I'm going to go ahead and give that one a star so it kind of stands out to us. And then another one says that the integral from a to a of f of x dx is equal to 0. And this is because since we're finding the area under the curve, if we start and end at the same place, there is no area. So that was why that would be 0. And then we also have the integral from a to c of f of x dx is equal to the integral from a to b plus the integral from b to c, and adding those two up since we can split area into two pieces and just add those two pieces together. The next example that we have says, given the integral from 2 to 0 of f of x dx equals 2, the integral from 2 to 4 of f of x dx equals negative 3, the integral from 2 to 4 of g of x dx equals 4, the integral from 0 to 1 of f of x dx equals 1, use the properties of definite integrals to evaluate the following. So the first one that we have, part A, is the integral from 2 to 4 of 2 times f of x minus g of x dx. So I'm able to take the integral of each of those terms individually, and that's by the first property up above. And I'm also able to pull out the k, or the constant value, which we have as 2 in front of our integral. So I'm going to go ahead and do both of those in the same step. So the first thing we're going to have is factoring out the 2. It's going to be the integral from 2 to 4 of f of x. Make sure you put your dx. If you don't have your dx, it's technically wrong. The reason why is because that's our width, and we need to have that on there. You need two things in order to calculate your areas. Remember, that's what we're doing. So minus the integral of g of x dx. And then from here, we know that the integral from 2 to 4 of f of x dx, looking up above, is equal to negative 3. So we have 2 times negative 3 minus the integral from 2 to 4 of g of x, which we also know is positive 4. And then working this out, we get negative 6 minus 4, or negative 10. So the next one says the integral from 0 to 4 of f of x dx is, looking up above, we don't have the integral from 0 to 4. However, we do have it going from 0 to 2 and from 2 to 4. So I'm able to split that up, and that is using that last property, property 6, up above. And so I'm going to rewrite this as the integral from 0 to 2 of f of x dx plus the integral from 2 to 4 of f of x dx. But the only issue is that I don't have from 0 to 2. I have from 2 to 0. So remember that one that we changed up there that had the error in it? I'm going to switch this and say this is going from 2 to 0. When I switch those limits of integration, the top and the bottom numbers, that's going to change that sign out in front, and it's now negative. So this is negative f of x dx going from 2 to 0 plus the integral from 2 to 4 of f of x dx. And now I can use this values up above. So it's negative from 0 to, or from 2 to 0, my value is 2, plus, and then from 2 to 4, the value that we have is negative 3. So this works out to be negative 5. Part C is the integral from 1 to 4 of f of x dx. And I do not have that looking up above, so I am going to go ahead and think of what I can do in order to get this. So I do not have the integral from 1 to 4. I do have it from 0 to 4 if I look at part B, but I need it to start at 1, and I can subtract away this integral. So I can take my integral from 0 to 4 of f of x dx, which we just calculated in part B, and I can subtract away 0 to 1 of f of x dx. And there's usually multiple ways to do these and still be correct. So if you ever figure out another way to do it, if you have questions, you can always email me or ask, and I can let you know if it's done correctly. You should still get the same numerical answer though. So our answer that we had from part B is, and I'll just draw a line from here to here so you realize that's where we're getting this from. This is going to be negative 5 minus, and then we have the integral from 0 to 1, which is just equal to 1 from up above. And so this works out to be negative 6. So why is these answers negative? Where would your graph be lying? It would be below your x-axis instead of above. The next example that we have says evaluate each definite integral. So the first integral that we have is the integral from 1 to 4 at 3x squared dx. So all we're going to do is take the integral just like what we did before. This is a 3, so it's just a constant, and then x squared. Integrating this would be x cubed divided by the same value. Again, we do not need to put our plus c because they cancel out, and you would see that if you did actually put the plus c. But I'm going to evaluate this from x equals 1, which is my lower limit of integration, up to 4. So simplifying this, 3's are going to reduce. I have x cubed evaluated from x equals 1 to 4. And by the fundamental theorem of calculus, we're going to evaluate this at the upper limit of integration. So that top number is going to get substituted in first, minus the bottom number substituted in second. And again, subtracting those. So 4 cubed is 64, minus 1 cubed is 1. So we get a value of 63. So part B here is the integral from 0 to 5 of the square root of x dx. So first thing I'm going to do is rewrite this and say this is the integral from 0 to 5 of x to the 1/2 dx. And then integrating this, I'm going to go ahead and add 1 to my exponent. And when I do, I get x to the 3/2. You can either divide by that value or multiply by the reciprocal, which would be 2/3. Again, I'm not going to put the plus c because it's a definite integral, but I'm going to put x equals 0, which is my lower limit, up to 5, which is my upper limit. From here, I'm going to substitute in that upper limit of integration. And so I have 5 to the 3/2. And if you want to rewrite this, you can, and I'll do that in a little bit. So I'm going to rewrite it as 5 to the 3/2 minus, and we have 2/3, 0 to the 3/2. So 0 to anything is just 0. And then we have 2/3, and you can always substitute that in on your calculator. But this is the same thing as a square root of 5 to the 3rd. I'm going to put minus 0. And when we work this out, 5 to the 3rd is just 125. And we can leave it as that. Sometimes they'll ask for you to round it so many decimal places, and you would just substitute it in to your calculator. And if you did, it's about 7.45. So we have some more examples on the next page. So part C says we're going to evaluate the definite integral from 3 to 5 of 2x cubed minus 3x plus 4 dx. So going ahead and doing this problem, we can take the integral of each term individually. And when we do that, that constant value can come out in front. So we would have 2 times, adding 1 to that exponent would be x to the 4th divided by 4 minus 3, which is our constant, times x to the 2nd divided by 2 plus 4x. And again, we do not need to use that plus c because we are dealing with a definite integral, and that value would just cancel right out. So I'm going to put it in parentheses, and I'm going to say evaluated from, and we're going to go from x equals 3 to 5. So from here I can simplify, and this would just be a 2 down here. So substituting in 5, I'd have 5 to the 4th all over 2 minus, I'm going to write the 3/2 out in front, and then 5 squared plus 4 times 5. I usually put this all in parentheses so I don't get confused. Make sure I have everything substituted in correctly. Minus, and then I'm going to go ahead and substitute in 3, my lower limit of integration. So I have 3 to the 4th divided by 2 minus 3/2 times 3 squared plus 4 times 3. Again, put that whole thing in parentheses since you are subtracting, and you will get the incorrect answer if you do not. Plugging that into your calculator, you can go piece by piece or just substitute the whole thing in. Just be careful with your parentheses. And we get a value of 256. Part D says the integral from 1 to 3 of 2 over y dy. And again, this is going to have a 2, which is my constant. And remember, 1 over y is the same thing as the natural log of the absolute value of y. And we are going to evaluate this from y equals 1 to 3, since y is my variable being used here. From here, using that fundamental theorem of calculus, I'm going to have 2 times ln of the absolute value of 3 minus 2 times ln of the absolute value of 1. So we have 2 ln of 3 minus, and ln of 1 is just 0. So we get an answer of 2 ln third. We have 2 more problems, part E and F. We're going to go in and circle those both, and we will work on those together in class. The next thing that we have is called a net change as an integral of a rate. So the integral of a rate of something from t naught to t1 is equal to the net change in something between t naught and t1. The net change in q of t, a quantity over an interval of time going from t naught to t1, is given by the integral. This is just the fundamental theorem of calculus. It's just written a little bit different. And so we have another example on the next page that we are going to go ahead and circle, and we will work together on this one in class.